Welcome everyone. My name is Sylvain Lézé from the Department of Aeronautics at Imperial College London, and this is the new episode of the podcast Turbulence at the Exascale. If you're not familiar with the podcast, we are trying to gather the view of the community regarding exascale computing for turbulent flows, not only, but mainly focusing on computational fluid dynamics. So this podcast is part of the UK initiative called ExCALIBUR, which is designed to harness the power of exascale computing in the UK. It is led by the Met Office, the UK Atomic Energy Authority, and the UK Research and Innovation. This podcast is also part of the UK Turbulence Consortium, which is a group of academics in the UK who are using Archer 2 to perform large-scale simulation of turbulent flow. So I'm very pleased today because my guest is Professor Ben Rogers from the University of Manchester. Ben has a chair of computational hydrodynamics since 2018, and his research activities include mainly smooth particle hydrodynamics methods, finite volume methods using low energy hardware such as GPUs. He has also interest in water waves and coastal hydrodynamics and shallow water equations and natural hazards modeling. So good afternoon, Ben.
Hello, Sylvain.
Very nice to have you on the podcast. And I will start by asking you if you can tell us a little bit more about yourself, where you are from, what you have studied, and how did you end up professor at the University of Manchester?
Yeah, so I'm originally from the UK, and when I went to university, I read engineering science at the University of Oxford, specializing in civil engineering, but it was also general engineering at the same time, which turned out in the long term to be very useful. And then after my undergraduate degree, I stayed on for a doctorate in sort of computer simulation of shallow water flows with professors Alistair Borthwick and Paul Taylor, who were my supervisors. And I really learned a lot from them, and they still inspire me today. But then after I finished my doctorate, I was very keen to spread my wings a bit. And so I went to the United States and did my first postdoc with Professor Tony Dalrymple, who's a specialist on water wave mechanics. And that really introduced me to this smooth particle hydrodynamics method, SPH. And then after that, I went to EPFL in Switzerland for a year, where I learned about large eddy simulation. But I had caught the SPH bug by that time. So a job came up as a postdoc in Manchester to carry on SPH research. And so I came back here in 2005, and I've been here ever since. So that's my sort of history, as it were.
Fantastic. So I was curious, how did you catch the bug of SPH, and how did you become, well, you said you started with a civil engineering background, but how did you become more focused on fluid flow and SPH in particular?
Well, my doctorate was looking at sort of coastal flows and shallow water flows, and we did that with the depth averaged or depth integrated approach, which means that you lose all the information that goes on in the vertical direction. And at the end of 3 years of studying that, I wanted to understand at a more fundamental level what was going on in terms of the fluid mechanics, particularly in breaking waves at the coast and things like this. And so I could see that SPH offered the opportunity to have a much greater understanding, looking at the three-dimensional flow features and the actual flow mechanisms. And so then when I started to go there into that field, I realized that there was an awful lot to do, and it was fascinating, and that it could challenge the existing methods that were struggling to simulate those sort of flows at that time. And so I really started to invest sort of time, energy, and effort into it. And it's fascinating both from a mathematical sense, but also from a physical sense. So there's a lot of sort of Hamiltonian dynamics in there at the same time as understanding what's going on mathematically and numerically. And that's perfect for me.
Good, amazing. So you've been at Manchester since 2005. So my next question is, what do you like about your job and working at the University of Manchester?
That has to be my close colleagues in the SPH group. So I will name them. So that's Professor Peter Stansby, Dr. Steve Lynn, Dr. George Fortakas, Dr. Lee Cunningham, and many others inside the SPH group at Manchester. So it's a really vibrant and active sort of intellectual environment that exists between us. And I really enjoy the interaction with my close colleagues there. I've also got, outside of there, a very wide network of international collaborators. And so I've been able to sort of stretch out from Manchester and from that group of close colleagues that I've got there. So I'm very lucky to have such good people to work with.
Great, amazing. Right, so let's crack on with SPH. I mean, most of our people who are going to listen to the podcast might not be familiar with SPH, and you are obviously a worldwide expert in this method. So can you briefly introduce this approach to us?
Yeah, I will try to do it in one sentence. They say if you can do it in one sentence, then you should know what you're talking about. So basically, SPH uses particles to represent a fluid or a solid or any medium. And these particles are allowed to move according to the local physical processes. And that movement is controlled by the local interactions of each particle with its surrounding neighboring particles. So that's the method in a nutshell. And of course, there's quite a lot of maths that underpins that, but effectively it just comes down to doing summations. So it's mathematically elegant and simple and addictive in that sense. So that's really the heart of the method.
Good, thank you very much. So now, I mean, I guess you have developed some SPH solver, and I think in particular there is one called dual SPH Physics or SP Physics. So can you tell us more about this this framework?
Yeah, so, well, everything in my field has got an SPH in it or a SPH in it. So that's why it's called Jules Physics. But actually, it's got quite a long history, basically going back to my first postdoc in the US. So when I arrived there, I was given an SPH code that had been developed for about a year. But we really started to push its development for coastal engineering applications. And gradually, one or two people came to visit, and the collaboration network started to get bigger and bigger. And then in about 2005, 2006, we were saying, look, we've put in all of this work into this code. Why don't we just allow it to be downloaded by people, and they can start to use it. And so it's not just kept to this very small group of people. So we did a preparation of what was basically the first open source SPH code for free surface hydrodynamics. And this was called Physics. So we just added the S on at the beginning of the word physics to give us the SPH. And we just thought that would be it, actually. We thought we might get 20, maybe 50 people downloading it, and it would be the community would carry on being quite small. But in actual fact, what happened is that a lot of people downloaded it. And after about 1,000 downloads, we realized we actually had to take it a bit more seriously. And so we really started to develop it much more rigorously and much more actively. So we released the first version in 2007, and that was written in Fortran. It was a serial code. Obviously, you couldn't do very large simulations at that time. And then we started to become aware of graphics processing units, or GPUs, and they are effectively mini supercomputers that exist in every computer. So we then started to develop a version of physics, of SPH, on the GPU. And so that took probably about 2 years. And so that was then released in 2011, again as an open source code. And that could be run either on the GPU, and it would run really quite fast, or it could run on a CPU with some OpenMP parallelization, and that would work pretty well. But the GPUs allowed us basically to speed up our simulations almost by a factor of 100 compared to what we were doing beforehand, and we were able to do much larger problems. So you could do this sort of simulation on your desktop, on your laptop. You didn't need to access a high-performance computing cluster or anything like that. So since then, Jules Physics itself has grown quite a lot. We've had a lot more collaborators come on board. And each time they come to us, they normally say, does Jules Physics or SPH do this? And the stock response is, well, it could do, but it needs development. And so then they start to collaborate with us and they help extend the functionality, or they improve some of the physics that's included in it. And so that's how the project, the Jules Physics project, has sort of gained momentum and has grown into this code now. So I mean, now with the latest version of the GPUs that we use, we can fit 80 million particles onto a single GPU that can fit on your desktop. And that's amazing in comparison to what we were doing just 10 years ago.
So I was about to ask you this. I mean, I'm glad you are giving this number of 80 million particles. So just to give us an idea, what domain size you could if you can give us an example of what you could do now with 80 million particles, that would be extremely helpful.
Well, that's a little bit like how long is a piece of string. It really depends upon the flow features that you're trying to resolve, because if it's a gravity dominated flow, then maybe you don't need to resolve all of the vortex motions that are important there in order to get the engineering quantities out that you're after. But if those vortex motions, for example, are important, then you obviously have to reduce the size of your domain to the point where the number of particles that we can fit on a GPU both captures the flow feature you're after and can actually be run on the GPU. So there's no such thing as a domain size for which we run it for. Every user has to look at their problem. They have to look at what GPU they have, because the computation is memory bound, and then they have to sort of work out how large a simulation they can run in how long a time in terms of the resources that they've got and what information they require from the simulation. So it's not a clear answer to your question, but
no, I think that's, of course, every configuration, every setup is different. So let's say if I want to start using your code, or if I want to start playing around with SPH methods, what will be the best strategy, you think?
Well, first of all, identify the application. Okay, so identify the application. So there are some applications for which SPH is clearly a good candidate. If, for example, you've got violent free surface motion, or you've got a lot of mixing going on in your domain, or non-linear motion, this can be with fluid structure interaction, SPH is a good candidate. However, it's not always the best tool for the job. So that's the first thing, is make sure you're using the right tool. And then before using the code, I mean, certainly what we do with our PhD researchers when we train them is we actually get them to write a little bit of their own code themselves first. So they understand what's going on inside the code, or inside SPH as a methodology. So we get them to write the SPH summation for a function and then for a gradient. This code can be in Excel, it can be in MATLAB, it can be in anything that the person is comfortable with. And then they truly understand it. And so then when they then take a big package like Jules Physics and apply it to their problem, they got a much deeper insight into what the code is doing and its limitations and also its advantages. So that's the process that we would take anybody who's new to SPH through.
And are you providing some training, or are there any tutorials available coming with the code?
Oh yes, I'm glad you asked. We normally conduct about probably about 3 or 4 training events each year to learn how to use the code. And then we've also done training courses specifically to understand SPH as a method throughout all of that. In conjunction with the code, we have a YouTube channel where we have got a range of tutorials, video tutorials on how to use the code, how to set up certain things, or how to use the post-processing to extract the data that you want. So we've got quite a few of these things around. We were wanting to run a session where we teach people genuinely how to modify the code for their own purposes. But we were about to run that, and then of course the global pandemic came along, so we haven't run that yet, but that's certainly in our list of things to do. And then the other thing I've mentioned is that we have these Joules Physics users workshops where we get the users along, the developers along, and the researchers all in the same room. So they're talking, saying, okay, SPH or Joules Physics did really well for this problem, and then somebody else says, but it failed for mine, and I don't understand why. So it's somewhere to talk and raise these issues and try and understand what things are done well, what things are not done well, and how we can improve.
Great, that's very good to know. So if we keep talking about SPH method, you recently published a manuscript about the grand challenges for SPH methods. So very simple questions. What are the grand challenges for SPH methods?
So SPH is a relatively new simulation tool or a technique, and this means it doesn't have the long background of people developing the method, understanding the method mathematically, and debugging codes and things like this. So it's still got a way to go to catch up to more established methods such as the finite element method or finite volume, finite difference, etc. So there are certain elements of the method that need to be strengthened. And because it's a new method and it's trying to do something that maybe some of the other methods struggle with, we have to be able to demonstrate that A, we can do everything that all the previous methods can do, and we can do all the new things that we say SPH is a good method to use. So we've identified sort of 5 grand challenges which will helpfully motivate the SPH community to work on and develop the SPH method so that it is genuinely competitive with the existing methods, as well as taking us beyond the state of the art. So these are, the first grand challenge is convergence, consistency, and stability. The second one is boundary conditions. The third one is adaptivity. The fourth one is coupling. And the fifth one is applicability to industry. So we think these 5 grand challenges they really capture the heart of what's needed to develop the method. They're not specific to one particular type of application. So for example, turbulence is not a grand challenge within SPH, even though it is extraordinarily challenging as a topic to investigate on its own and then within SPH as well. And so the idea of these grand challenges is really is to focus the research efforts of people around the world to try and push SPH to be as good as it should be and competitive with all the other methods that already exist.
Good. It's quite a challenging task, I believe.
But there is an international prize that we award every 2 or 3 years, named after one of the people who invented the method. So this is the Joe Monaghan Prize. And we award that to a publication or a piece of work that's taken place in the last 6 or 7 years in that sort of time frame that's made a significant advance in one of these grand challenges. So we try to sort of motivate and reward at the same time.
That's a great initiative. So talking a little bit now about exascale computing, once again, a very simple question with probably a more challenging answer is, would you say that SPH methods are ready for exascale computing?
I think, yes, they are. And I think they're an ideal candidate. And I'll explain why. So around each particle, you have this, what I call it, a radius of influence. Okay, so one particle will interact with all the neighbors inside that radius of influence. And the particles outside of that radius of influence, it doesn't interact with. So that means it's got a finite number of neighbors around each particle when you're doing the summation. So this is very useful because basically we can create a vector list of neighbors, and then we can put that through a machine of multiple processors. And this makes it ideal for parallel processing as a general technique. Obviously, there's going to be very specific challenges with exascale because we're only just beginning to see the first exascale machines come online, and their architectures are very heterogeneous. They're a mix of lots of different types of GPUs and CPUs and everything else. So working out how to take a method and put that onto an exascale machine of heterogeneous architecture types is a challenge. But I think SPH is an ideal candidate for it because it has this compact support, or this radius of influence where you've got a limited number of neighbors. So I think it's an ideal candidate for it.
So what is the largest number of GPUs or CPUs that were used, for example, with dual physics?
Well, we published a paper it must be about 8 years ago now, where my colleagues at the University of Vigo in Spain, they ran a simulation with 64 GPUs, and this was run on the Barcelona supercomputer. And so that was 64 GPUs, and we did that for 1 billion particles, which was the largest simulation for free surface flow with SPH at the time. So that's the number that I'm aware of. I'm not aware of a larger simulation or using a larger number of GPUs. But so, I mean, that was really just sort of an exploration in one sense of can we do it? And we demonstrated, yes, we can. Can we do it better? Oh, for sure. But the hardware is also developing quite fast. And so we have to sort of change some of the methodologies if we want to go to exascale.
Great. And let's say if you have access to a supercomputers tomorrow, and if you can run your simulation using the whole supercomputer, what would you be able to do that you cannot do at the moment because of resources restrictions?
That's a great question. There are lots of problems where basically people say, oh, if only I had more computational resources or computational power, we could investigate this particular feature of the simulation. And some really good examples basically come from, for me, in coastal engineering, looking at tsunami flows. So when tsunami flows come in, they inundate a very, very large area. But of course, tsunamis are not pure water, okay? They are a mixture of things. And SPH is a method that does mixing of different species very, very well. And so it would be fantastic to be able to use SPH to investigate some of these things, to understand the phenomena better, or to understand, for example, how to advise the local population to design or construct their buildings so that they will survive. And so having an exascale simulation to explore that kind of space and try and understand it and then provide guidelines is one example. Another example is in sort of the process industries. They've got a lot of applications there where you're looking at mixing of lots of different quantities, and the physics gets very complicated, particularly when you've got thermal effects which come in and complicate that sort of thing. And so, the complexity just keeps on getting greater and greater and greater when you dig into these applications. So there are many, many applications that we can do, and those are just two of them, I think.
Great, thank you very much. So you have been in Manchester and in the UK since 2005. So this is a more broader question. I mean, you're obviously interacting with colleagues in Manchester who are doing, I will say, more conventional, who are using more conventional methods. And I was wondering if you could tell us if you think that the CFD community is ready for the next generations of supercomputers, and obviously for the exascale era.
My honest answer is no, I don't think we're ready. Okay, so I think what you've got is you've got a number of groups around the UK, but also around the world, who have identified this early and have been preparing for it early. But on a broader scale, and we need to think about preparing our engineers for the exascale era. So, that takes place at many different levels. It's not just at the research and development level, at PhD and postdoc level. It's also from sort of year one of our engineering degrees. We have to open up the eyes of our students to understand what's possible, but we also have to equip them with the skills to be able to do that. Now, exascale machines, they are the most advanced that we'd have ever seen, and developing the skills to use those in a useful way, that's a really important thing that we've got to do. We can't just leave it to the point where the engineer leaves the degree, they finished, hooray, they've got their degree, and then they go out and say, whoa, what's an exascale machine? We need to be educating people from a much earlier stage, I think, in order to prepare them for exascale. And if you think about it, the exascale era is going to last quite a long time. We've taken quite a while to get there, but it's also going to last probably at least a generation. So we need to prepare our engineers and our users to be able to do that. But in my opinion, there's no point developing exascale technology if the engineers can't use it, or people can't use it to do really important turbulence flow or astrophysics simulations. So there's a very, very strong educational element there in preparing the whole community for that. The other thing that we should think about is access. How do we make sure we give access to the people who are going to make the best use of these facilities? It's wonderful doing these fantastic demo cases, but if that's all they stay, if they stay as just a demo case, then there's a bit of a problem there for me, and there's a lot of effort and energy in going into that sort of thing. So I don't think we're ready yet as a community, and I think we've got some work to do.
Good. We're going to be busy. I have two more questions. My next question is, if there is one thing that you could change about high performance computing, I'm thinking mainly about hardware. So what would that be? I know you mentioned you're mainly memory bound, but if you can expand a little bit, or if you could change one thing, what would that be?
Make it easier to program. Because most of the time, the people who are doing the PhDs with us, for example, or the companies that sponsor work with us, they have a very specific application in mind. But the people who are programming or creating the next generation of simulation codes, they're having to wear multiple hats all at the same time. They're having to wear the hat of an engineer understanding the physics of the situation in the broader context. They have to wear the hat of a computer scientist understanding everything that's going on inside the machines and everything that goes on there with computer hardware. And then they also have to wear the hat of a mathematician trying to understand the behavior of the solutions when they finally come back. So, HPC programming, it's a very, very high level skill. And if I could change one thing, it would be make it easier to program. That's a lot easier said than done, but that's the one thing I'd like to change, so that people could perhaps focus a bit more on using HPC to solve their problems rather than learning about memory hierarchies and things like this.
Great. I think everyone will agree with that. What my last question is, so we are talking this day a lot about exascale computing, and But I would like to have your opinion on what will come maybe in 15, 20, 25 years. Do you think the hardware will look the same? So more powerful GPUs, less energy or more energy efficient, more powerful CPUs, more cores? Or do you think we are going to witness a revolution, maybe with quantum computing or I don't know, other things? What's your view on that?
Before we look forward, let's look backwards. So if you go back to the early 1990s, okay, the supercomputers that they were using then, they had less computing power than my mobile phone, which fits in my pocket.
Mm-hmm.
Okay, so if you were to sort of extrapolate that sort of development forward by another sort of 20, 30 years or something, then what form the hardware will take is a very interesting question. So I honestly don't know the answer to that. For the last 10 years, people have been talking about integrated CPUs and GPUs in terms of trying to achieve higher performance or larger simulations or whatever. But they still haven't quite arrived in the way that people have been talking about or dreaming about. And so I suspect that trend will increase, but there's been some resistance over the years to going that way. So I honestly don't know. I think quantum computing is very exciting, but it's also been very exciting for a long time. However, I'd say in the last 5 years or so, there's been some fairly major advances in quantum computing in to the point where it actually exists now.
Mm-hmm.
Okay, yeah. It might be a few qubits that people are adding together, but it actually exists. And so if you fast forward 20 years or so, then it could well be the genuine new kid on the block that can do proper simulations, and that is wonderfully exciting as an idea, and that would really change what we're able to do now. However, I've got one concern about the future, which is the energy consumption for all this high performance computing. So one of the reasons we went with GPUs so early was because they use far less energy for the same simulation size compared to using some kind of computing cluster. But if you look at the exascale machines that are coming on board now, the amount of energy that they require is enormous. So that possibly is the biggest technological barrier to overcome, is the energy required to run these massive computing resources. So quantum computing might come to our aid, but we're not sure how we might be able to do that then. So I think the future is very exciting, and it's going to change a lot, I think, in the next 20 years.
Great. Thank you very much, Ben, for your time and for your input. And of course, we would like to wish you all the best for your future endeavors around your SPH methods, which seems to be very promising and exciting, especially for exascale computing. Thank you very much all for listening to this podcast. As usual, the recording will be made available on the UK Turbulence Consortium website, and on the links will be posted on Twitter. It's UK Turbulence in one word, very easy to find on Google. So thank you, Ben, for your time again.
Thank you, my pleasure.
And hopefully see you very soon for another episode of the podcast.